All right, I'm back. We are on page 250 now, and we're basically doing the same thing that we did last time, just for practice. So what I did, because I didn't want to waste more of your time than I'm always wasting by just like going on and on, as I'm doing now, is I went ahead and I already found the interesting x values. So why are they interesting? I feel like as a person who hasn't encountered interesting values, you're likely to think that the ones that I picked are interesting. And I think that there are two more that you might be really interested in. And then there are more that maybe you should be interested in. So, like things that didn't make the cut, let's look at. So, I'll highlight them. I'm going to highlight things that didn't make the cut. So, the following points are interesting, but not from a limits standpoint. So, this point is kind of interesting. That's not a good color at all. Like you can hardly even see it. This point is kind of interesting, right? Something's happening there. Curve is like doing a weird thing. That's interesting. This point is interesting. The curve goes from increasing to decreasing. So that's interesting. Here, similarly, it's interesting, but not from a limit standpoint. The next most interesting point that didn't make the cut is actually right there. Like, what is going on? It's like we took one type of thing and then instantly changed, not smoothly, just like abruptly changed from like this to like, boom, this. That's weird. And there's another point like that right here. And then this should be interesting, 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 interesting. All of those points are very interesting, but they're not interesting from a limits standpoint. They're interesting for another. Oh, there's another interesting one actually. Right around here, there's an interesting point. They're interesting, I don't know, from a certain standpoint, but not from a limit standpoint. So now let's do our limits. So the first actually interesting point moving from left to right is negative 28. So negative 28 is this first vertical asymptote on the far left. And you can see that as you approach from the left, you're going to go to infinity. As you approach from the right, look at this, you're definitely going to negative infinity. So I'm going to fill in both of those. The limit as x approach. Oh, and now we have to correctly write it out. So that's good. The limit as x approaches negative 28 from the left of f of x is infinity. And then we also said the limit as x approaches negative 28 from the right of f of x is negative infinity. All right, so if the limit from the left doesn't equal the limit from the right, then the limit does not exist. So I'm going to write the limit as x approaches negative 28 of f of x. So saying without a plus or a minus there means the little like superscript means that you're overall making a claim about the left and the right. So I'm just going to say dne. A lot of people say equals dne. I could live with that. It's not a problem. So dne, it does not exist. How about the value of the function? If we look at it, there's no solid dot anywhere. So that also does not exist. So I'm going to say f of negative 28 does not exist. Again, I could live with equals does not exist because you're just kind of like on, you just get going, All right, negative 24. Negative 24, let's go from the left, is here. Let's go from the right. I don't even know what that value is. I'm just going to do this part first. From the right is there. All right, so both of those appear to be equal. I mean, they're definitely equal. They both equal 12. So let's get that down. We got the limit as x approaches negative 24 from the left of f of x is, I think I said 12. And then the limit as x approaches negative 24 from the right of f of x is also 12. That's a big deal because the limit from the left equals the limit from the right. So the limit exists and is equal. So no plus or minus this time of f of x is 12. If we can also say that f of 12 is equal, nope, sorry. If we can also say f of negative 24 is equal to 12, then the function's continuous there. If not, there's a removable discontinuity because the limit exists but doesn't equal the value of the function. So at some point we'll get to that in the notes, and then you'll be like, man, we've been saying that over and over. Yes. At x equals negative 24, we're down at negative 4 for some reason. It always reminds me of the original Super Mario Brothers, where, and probably many subsequent, where sometimes you would like jump and you would land on a brick, and then the brick would start like shaking, and then it would just plummet down. That's what that part of the graph looks like to me. That specifically is what it looks like. I've always thought of limits in terms of a Super Mario side-scrolling game where you're like moving from left to right, and then sometimes you can move from right to left, but not always. I think it was Super Mario 2 is like a weird game. 3 is a lot like Super Mario 1, but like way more options. That's like when I think of games, I think that was the best original Nintendo game. You know, share in the comments what you think was the best game. All right, here we go. Definitely going to negative infinity there. Here we go. Also going to negative infinity. So that's exciting because we're going to be able to say that the limit as x approaches negative 20 is negative infinity. So the limit as x approaches negative 20 from the left of f of x is negative infinity. The limit as x approaches negative 20 from the right of f of x is negative infinity. Woo! That's exciting because they're the same, which means we can say the limit as x approaches negative 20 overall of f of x is negative infinity, which is so much information. If you tell me that, I instantly know what the graph looks like. Just diving down, we know what it looks like. Is there a random point? There is no random point, so f of negative 20 does not exist. F of negative 20 does not exist. If there had been a solid dot somewhere on there, we would have just said f of negative 20 equals wherever that dot was. Didn't happen. Moving on to negative 10. All right, negative 10. I feel like once you get the gist of this, not really that bad. There's from the left, from the right. Both of those are approaching negative 8, so that's an exciting moment. We'll get to say that the limit exists. Limit as x approaches negative 10 from the left of f of x is, I think I said negative 8. I hope I said negative 8. I'm going to go with that here. You know, correct me if I'm wrong, but you're not here to do that. So what are we going to do? Okay, let me just check it now that I've written all of that. Yes, definitely negative 8. All right, they're the same. So we can say that overall the limit exists. Limit as x approaches negative 10 of f of x is negative 8. This would be a really good page for you to like try to do on your own and then watch the video if you need it. If you don't need it, I won't be insulted, although I'd hate to think I'm doing all this work for nothing, but who knows, right? So f of negative 10 is this solid dot that's up here, right? So f of negative 10 is actually 2. So this is a removable discontinuity by definition. So the definition of a removable discontinuity is the limit exists and is finite and isn't equal to the value of the function. The value of the function might exist, it might not exist, it doesn't matter. If the limit exists and is finite and is not equal to the value of the function, that's the definition of removable discontinuity. You've seen those before in Algebra 2, maybe in math analysis earlier in the year. It's when you have like a factor in the numerator and denominator and they cancel, you get that removable discontinuity. All right, let's look at 10. All right, x equals 10. This looks good. I'm not gonna go the full distance here. Let's just pick up our journey here. So negative 4 is definitely the limit from the left. From the right, you can see you're gonna get the same thing. You make the turn. Okay, that person expects to also get negative 4. So let's fill those in. We can fill in the overall limit. Limit as x approaches 10 from the left of f of x is, I think it was negative 4. Yes, it is. Okay, and then the limit as x approaches 10 from the right of f of x is also negative 4, which means the limit from the left equals the limit from the right, which means the limit exists. So the limit exists, and is -4. Limit. One thing that will happen a lot is that the limit won't equal the value of the function. Like it, in general, in life, that all the time the limit pretty much equals the value of the function, but it's not interesting when that happens, and so no one really asks you about it. It's one of those things like no one ever comes up to you and like said, you know, at an icebreaker thing at the beginning of a class, no one's ever like, come up with the 3 most mundane things about you. Like, what are the 3 things that you do that literally everyone else does? Like, okay. So like that's what happens when the limit equals the value of the function. It's like very mundane. That happens almost all the time. So the questions you get asked are actually about other things. And so you get this sense that like limits don't exist or limits don't equal the value of the function very often. Not the case. It's almost always the case that they do. Just we're really interested in the weird things. All right, at 10, the actual value is way up here at 12. So f of 10 is 12. All right, so that's another removable discontinuity. We got them all over the place here. What's our next thing? 20. We're getting there. We're almost done with this one. All right, 20, we see what's happening here. From the left, we're going up. That's going to go to infinity. From the right, on the other hand, it's going toward negative infinity. All right, so let's fill those in. And then because one's going to positive, one's going to negative, limit doesn't exist. The limit as x approaches 20 from the left of f of x is, what did we say? We said infinity. And then the limit as x approaches 20, whoops, 20 from the right of f of x is, we said negative infinity. You'd think I would be able to remember that because I made a big deal about how the limit doesn't exist, but it's hard. The limit, saying that the limit doesn't exist is like, it's information, and that's good. But there's a lot of ways the limit cannot exist, right? You could go like this, and then woo, way up like this, have infinity from one side and finite on the other. You'd have 2 different finite things, 2 different finite things, like what this, like there's so many options, which is why like it gives you info, but it doesn't give you anything definitive. So like you need more, which is why you need the limits from the left and the right. Like they're more important when the limit doesn't exist, because otherwise you just don't know anything. Like why doesn't it exist? And then let's look and just see at 20, there's no like random dots or anything. So f of 20 does not exist. I have this weird suspicion I've been saying 10 too often. Like maybe I haven't been, I don't know. X equals 40 is the next one. It's like sometimes my brain just, oh, what is that value gonna be? All right, it looks like it's 8. All right, let's go. From the left, here we go. And we definitely get 8. And then from the right, go through these 2 interesting points that didn't make the limits cut. But they're interesting because the function's changing, increasing to decreasing and then to increasing. Also, you can't really see that unless I move it. I think that's really interesting, but not in terms of limits yet. So both of those gave me the same y value. That y value I think is 8. So the limit as x approaches 40 from the left of f of x is equal to 8. And the limit as x approaches 40 from the right of f of x is also equal to 8, which means that the limit as x approaches 40 is 8. And that's exciting because this is really about limits. The whole like function value column, we actually do not care about. We're just doing that to like remind ourselves of what it means. But we don't care what those values are right now because we're talking about limits. When we start talking about continuity, we'll really care about that. But until then, it's all about what should it have been. It's weird. They're very very ivory tower, pie in the sky kind of idea. Like perfect world scenario, what do you think would happen to this function? In a perfect world scenario, the value at 40 should have been 8 because then the people from the left and the people from the right would agree and everything would be happy. But instead, what is happening there? Instead, nothing happens there. So I don't know what kind of message you get out of this, but we definitely know that f of 40 does not exist. We got a lot of not existing things. All right, so the notation is huge. In calculus, this is weird. We basically have started calculus. Limits are the beginning of calculus. In calculus, you often know the answer ahead of time, and it's all about how you present that answer, right? You have to justify it. Like you have to prove things, you have to come up with these ironclad explanations that no one could look at and be like, well, yeah, but what if? Like, oh no, I'm telling you that the limit as x approaches 40 of f of x is 8 because the limit as x approaches 40 from the left is equal to 8, the limit as x approaches 40 from the right is equal to 8. You can't argue with that anymore. That by definition now, that limit exists and it's 8. All right, so I'm going to cut off here and I will be back in the next video, probably in a different shirt, but who knows. And I will see you then, and I hope you are finding these helpful.